Buffers. This is usually the last topic in the acids and bases unit, and probably people's least favorite. It's pretty complicated to wrap your head around. I think in practice the questions are not actually that difficult on this topic, but let's dive in and do our best. So the definition of a buffer is something that can resist pH change with small additions of acid or base. So somehow a buffer is a substance that can neutralize both acid and base. So in a way it's amphoteric, something that we've talked about before. Now buffers are super important. They have all sorts of applications or relevance in things like bodies of water and inside of your body and things like that, but I'll let you read through this page to get those. I'm going to focus more in on the sort of chemistry behind it. So a buffer works because it can neutralize both acid or base, and really just small amounts. It can't do so indefinitely. A buffer's capacity is how much acid and base it can neutralize. Now, if you're going to be able to neutralize acid, you must contain base. And if you're going to neutralize base, then you must contain acid. So that means somehow a buffer is something that contains both of those things. So some of those things that we've seen previously that are amphiprotic, something like hydrogen carbonate was an example of an ion that was amphiprotic because it had this proton, this hydrogen still, that could be donated to act like a Lewis acid, but it also has a negative charge, which makes it a good proton acceptor. And so those amphiprotic substances that we've talked about can, in some cases, act like buffers. So hydrogen carbonate actually forms a buffer inside of your blood, and it's in equilibrium with water and dissolved carbon dioxide. And this is one of the ways that your blood maintains its pH, is with the presence of this ion in your blood. But for our topic here, it's less going to focus on those amphiprotic ions, although they can act as buffers. And it's going to focus on these mixtures that we can produce with our weak acids and bases. So it's important to note that we can have acidic buffers, where the pH that is maintained is below 7. And we can also have basic or alkaline buffers, where the pH is maintained at some pH above 7. Okay, now, there are two different ways, two different methods really, to create a buffer in the lab, or at least that the IB wants you to know about. Now, I'm actually going to skip ahead to method 2 because it's one that we've already seen when we did titration, and then I'll come back to method 1. I'm going to skip all this part on method 1, and I'm going to skip ahead to the pages where it talks about method 2. So in method 2, this is essentially our titration of a weak acid and a strong base. So one key thing is that when we make these buffers, we're never going to have any strong acid or base left in the mixture. But we can use strong base to neutralize some of the weak acid. And if you think of it from an ice baby perspective, let's start off, just use simple numbers that if we take a weak acid and we have 1 mole of it in our container, and if I then add half a mole of the strong base, we know that the strong base will be completely used up and consumed because it's the limiting reactant. I'll have 0.5 moles left of my weak acid. I'll have none of my strong base left. So that's key. The strong base, if you're going to make the buffer this way, what I'm calling method 2, you need to make sure that the strong species is by far the limiting reactant. Okay, now in this type of reaction, combination of a weak acid and a strong base, we know is going to make a slightly basic salt as the product. We get the Na plus from the base, and we get the CH3COO minus from the weak acid. This is our basic salt. And really it's basic because of the ion of this CH3COO minus, that conjugate base of the weak acid has some basic character to it. And if you think through the ice baby calculations, you'll note that we've created 0.5 moles of it, We've also made water, but that's not particularly relevant right now. So if you see what happens, we end up with half a mole of weak acid in our solution, and we end up with half a mole of its conjugate base in solution. And so what we've done is we've created a solution where we have equal amounts of weak acid and weak base. And that's what creates a buffer. You don't want to have strong acids or bases present. You want to have a system that's at equilibrium that contains both acid and base. And so the way to do that is with a conjugate acid-base pair. So this method was we use an excess of something weak, so excess of weak acid, and then we add a limiting amount of strong base. And the best amount that you could add would be exactly half the amount that you had of the weak one. If you add exactly half, like I did in this instance, we end up with exactly equal amounts of weak acid and conjugate base. So their amounts are equal, and that means that I can neutralize equal amounts of base and acid. So that it kind of makes it an ideal buffer. It has equal buffering capacity against both acid and base. If we had only added 0.4 moles, for example, we'd have 0.6 moles of our weak acid left, and we'd have 0.4 moles of our conjugate base formed. It would still be a buffer, but it would be sort of leaning towards the acid. It would be better at neutralizing base than acid. But the result is that we've made a buffer. Now, when you actually try to write out what a buffer is, you can't just usually label it with one chemical formula because it's actually an equilibrium. And the tricky or confusing part is that it actually looks just like the weak acid equilibrium, because the thing that makes it a buffer is the weak acid here and the conjugate base that's here. Now the difference between a regular weak acid and a buffer is that in the buffer there's actually a lot more of the conjugate than there would be if it was just a weak acid. We know that it very partially dissociates. It would mostly be in the weak acid form. So in the buffer, and that's not really represented in the chemical equation. That's why this confuses people so much. It's so hard to remember how to represent it. But this equilibrium represents the buffer, and you've got these two things in equal amounts. That's what makes it a buffer as opposed to just a weak acid dissociation equilibrium. So there has to be some writing to describe that both of those things are present in more or less equal amounts. So the chemical equation on its own probably wouldn't be enough. So you can use the chemical equation, but then add to it that you've got equal amounts of those two species. That's what's making it a buffer. Now, one of the questions that throws people off the most is they say, okay, illustrate how it could act as a buffer. How could it neutralize both acid and base? So let me try to shrink it down, give myself some room. Okay, so the way you illustrate is, for example, or you can describe, you're going to basically describe equilibrium concepts of Le Chatelier's principle. If we add acid, that equals, we're going to add H+. If we add H+, we'd say that H+ reacts with the conjugate base, the ethanoate ions. It's going to cause a shift left, produces the ethanoic acid molecule. But so basically any H+ that is added will get neutralized. So the pH won't really change much. It will change a tiny bit, but not the same as if it was just added to something like distilled water. So this is a H+ is neutralized, and you get minimal pH change. Okay, so what happens if we add base? Well, if we add base, we should associate that with adding OH-. That's a little trickier. OH- is not written in this equilibrium, but we should know that when OH- and H+ are put together, they will react and form water, and they will neutralize each other. So OH- reacts with H+, forms H2O. Okay, well, that doesn't really help us yet, but step 2 then of how this buffer works is that because we just removed something from the right-hand side of this equation, the ethanoic acid will dissociate or shift right, and that produces an H+. So the OH- removed an H+, but the equilibrium shift produces an H+ to replace what was lost. And so in the end, you get minimal pH change. So people often struggle. That's probably the hardest type of question related to a buffer is they say use a chemical equation to explain how the buffer works. How does the buffer actually maintain the pH? And it's basically just equilibrium concepts. You can add either H+ or H-, and they will both get neutralized, and the amount of H+ in the solution will stay more or less controlled, stay more or less constant, so the pH does not change much. Okay, we can also, this was the creation of an acidic buffer because we began with one of our weak acids, and then we have a weak acid plus its conjugate base. We can do the same thing to make a basic buffer. If we start with a weak base, like ammonia, and we produce an acidic salt, which in this case would be NH4Cl. The NH4 plus is the conjugate acid. Again, if we do the 1 mole and half mole thing, when we're at equilibrium, we'll have equal moles of the weak base and the weak acid. So we could try to explain the buffer action like this. We'd probably end up we could write it like that, or more likely, we'd probably kind of show it almost as the dissociation, like this. And then what separates it from just a simple dissociation of a weak base equation, well, it doesn't look any different, but in our explanation, we would talk about how the molar amounts here, if they're not half a mole each, but the mole amounts are equal of the weak base and its conjugate acid. And then we could talk about what happens if OH- gets added, how it shifts to the left. And if H+ were to be added, H+ could react with NH3 and could turn into NH4+. And so either way, we can neutralize whatever is added to a certain degree. Okay. Now, I skipped method 1. So in the method that we just did, we had starting with something that's weak and in excess, and then we add about half the moles of something that's strong, and that neutralizes about half of the weak species, and then it creates an equal amount of the conjugate species, conjugate acid or base. However, you can do it another way. What I call method 1 is that you start with a weak acid or base, and then you can just add that conjugate directly by adding a salt that contains that ion. We've talked previously about salts that have acid-base character, that salt hydrolysis topic. So this is just playing off of that. So for example, if I have a weak acid like ethanoic acid, shown up here on the left, CH3COOH, its conjugate base is the ethanoate ion, CH3COO-. Well, a salt that's really soluble in water is sodium ethanoate. So you have this weak acid, which only partially dissociates, and so is mostly weak acid. You take this salt here, sodium ethanoate, which is really soluble, so it fully dissociates, gives you lots of these ions, and then you just combine those two things. So if you took a weak acid solution and you just dumped a bunch of this salt into it, you would get a mixture that had about equal amounts of both the weak acid and the conjugate base. So now you've gotten to the same place by adding the ion, the conjugate base, from its own substance, from its own salt. And that would then produce an acidic buffer. The next page talks about the example we used before. You could do the same thing, start with a weak base like an ammonia solution, and then find a salt that contains its conjugate acid, the ammonium ion, like ammonium chloride, which is really soluble, gives you lots of that conjugate acid ion, and then you end up with a mixture that has about equal amounts of both NH3 and NH4. Okay? So probably the most common question about buffers is just questions about how do you prepare them, how do you make them. And so there's two different ways. There's they always have a weak acid or base and the conjugate, but you can either add that conjugate directly from a salt, or you can do the method we started on, which is you can play off of the ice baby calculation and use a limiting reactant amount of something that's strong to neutralize some of your weak species and to create some of the conjugate. And then that's how you end up with a buffer. We actually saw these buffers, if I skip down the line, when we were doing titrations with weak things against with strong things. We saw that they did this funny curve, something like this, where the pH started to rise and then it kind of leveled off for a while. And then it went up really quickly again by the equivalence point. Now we talked about how the equivalence point was above 7 because the basic salt that is produced. And I think we mentioned something about the half equivalence point. This is called the half equivalence point. And at the half equivalence point was where we have equal moles of CH3COOH, the weak acid, and we've produced the same amount of its conjugate base. And so at this point, notice that around this point, the pH has kind of leveled off. It doesn't change much. That's because at the half equivalence point, you've created a buffer. And so you get this kind of buffered region here around the half equivalence point where the pH doesn't change much despite the fact that you're adding more and more base to it, or more and more acid if we were looking at a base and acid example, around that half equivalence point, because at the half equivalence point, we have equal moles of weak acid and conjugate base. And so at that point, we've created a buffer. So it's one last little detail that they could ask you about on the titration curves. So that's the topic of buffers. We haven't really looked at calculations with them. We'll hold off on that for now. This is the conceptual part about how they work, describing that in terms of their equilibrium, shifting left and right, and thinking through how we could prepare them from different combinations of substances.